Monolith reactors offer several advantages over conventionally used slurry bubble columns, airlift reactors, and trickle bed reactors for a wide variety of process applications. These advantages of monolith reactors stem from the uniquely structured multi-channel configuration as pictured here. The advantages include low pressure drop, high gas liquid mass transfer rates, minimum axial dispersion. The channel diameters may range from 1 to 5 millimeters. And monoliths can therefore be viewed as a structure that is comprised of many repeating building blocks, where the basic building block is a single channel. It can be argued that data obtained from studies on a single channel, or what may be called a capillary, can be used in scaling up a monolithic reactor. This, of course, is based on the premise that the gas and liquid distribution through all the channels is uniform. The objective of the presentation today is to give you some qualitative insights into the gas-liquid flow inside monolithic structures. In particular, we focus on what is normally termed as Taylor flow. This is named after Sir Geoffrey Ingram Taylor. To set the scene for hydrodynamics in a monolithic reactor, let us have a recap of the hydrodynamics of bubble columns, where a gas is dispersed as bubbles inside a liquid or a slurry, and the column may have internals such as heat exchange tubes in case of highly exothermic reactions such as the Fischer-Tropsch process. This is an airlift loop reactor where we have a gas and liquid upflow in the central tube, and the gas is disengaged and the liquid flows down the downcomer. So this is the central portion is called the riser, and we have a downcomer. The airlift reactor could also have heat exchange tubes, and we have a liquid inlet here and a liquid outlet here. A monolith reactor configuration is one in which the riser portion of the airlift reactor is replaced by a monolith bundle, and there is gas and liquid upflow inside the multi-channel of the monolith construction. The gas disengages at the top, and the liquid is recycled back to the inlet. Let's have a look at the video recordings of gas and liquid contacting in bubble columns, airlifts, and monoliths. Start with a bubble column. We have the range of bubble slices, large, small, dispersed in the liquid. There's a high degree of backmixing in the liquid phase. This regime of operation is relevant to the Fischer-Tropsch process for synthesis of hydrocarbons. Let's look at airlift. We have due to co-current flow of gas and liquid, the bubble sizes are more uniform, and on average they are significantly smaller than that in a bubble column that does not have co-current upflow of the liquid phase in normal operations. Let's look at gas entering a monolith construction here. There's nothing too very much to see in this video. Let's look at a different view of the monoliths. We can see there are some cracks in the monolith, and you can see some gas bubbles going up. But we're going to focus on gas and liquid flow inside a single tube. This is a ceramic monolith. Here is a monolith with square channels made of ceramic material. It is common practice to quote the number of channels per square inch of the monolith. This structure here has 49 CPSI channels per square inch. This is a glass monolith constructed of circular tubes. Such a construction is commonly used in laboratory experimental studies, but not for industrial applications. In this case, we have a 35 CPSI with a void fraction of 40%. Monoliths up to 600 CPSI can be constructed and can be purchased. The inside of a single channel is usually coated with a catalyst that is important for liquid phase reactions. Let us gain our first glimpse at gas and liquid flow inside a single channel of a monolith construction. Gas and liquid flows upwards, and we focus on the gas flow and liquid flow inside a single channel. We see bullets or slugs of gas bubbles that move as a kind of a bubble train. This bubble train flow, consisting of slugs following one another in a uniform manner, is termed Taylor flow. And this is a unique flow structure that is responsible for the superior performance of the monolith reactor. I point you towards these references that give further details of the hydrodynamics and mass transfer in Taylor flow. Depending on the relative velocities of gas and liquid upflows inside the single channel, we obtain a variety of flow regimes. And to illustrate that, we will look at video recordings of 3 different cases in which we have water as a liquid phase, ethanol as a liquid phase, and oil as the liquid phase. And in all cases, air is the gas phase. These recordings were made for a 3 millimeter diameter circular capillary made of glass, so that the flow regimes can be visualized and recorded using a high-speed camera. Let's first look at water and the bubbly flow regime. This flow regime typically occurs at relatively high liquid velocities and low gas velocities. It is characterized by the presence of relatively fast-moving bubbles, and the diameters are less than or equal to the diameter of the capillary. To increase the gas velocity a little bit, we obtain the slug bubbly flow. We have a slug and the bubbles. For a well-defined set of conditions, we have the bubble train flow with the length of the bubble equal to or longer than the diameter of the channel, and the distance of separation between two bubbles is practically the same. It's flattened at the bottom and hemispherical at the top. This is the bubble train or Taylor flow. This is the most desirable flow regime for use in monolith reactors. Increasing the gas velocity further, we have the churn flow. Very, very long elongated slug. And if the gas velocity is increased further, we have a central portion that is just the gas phase, and we have annular flow. With a liquid such as ethanol, we have more or less the same kinds of flow regimes. Bubbly flow, slug bubbly flow, Taylor flow, the one to aim for, churn flow with long elongated bubbles. Remember, this is with increasing gas velocity along the horizontal direction. We have annular flow at very high gas velocities. If you use the viscous liquid as the viscous oil as the liquid phase, the slug bubbly flow regime is difficult to realize, and we have just 4 of these regimes. Bubbly flow, Taylor flow, there we see the and annular flow. This graph shows some experimental data on gas liquid mass transfer, in particular oxygen mass transfer from the gas phase to the liquid phase in 3 different monolith constructions. 1 millimeter channel dimensions, 2 millimeter channel diameter, and 3 millimeter channel diameter. The mass transfer coefficient is significantly improved if the channel diameter is smaller Here are some conclusions that emerge from our experimental studies on monolith reactors. A monolith loop reactor performs better than a bubble column or airlift loop reactor from a gas-liquid mass transfer point of view. But of course, there are other considerations like heat transfer that might mitigate against this advantage, because it's more difficult to remove reaction heat from monolith constructions. It also has other advantages in relation to bubble column slurry reactors, because there is no need to filter the catalyst particles, because the catalyst is introduced as a thin layer coated on the inner surface of the single channel within the monolith construction. The smaller the channel dimension, the better the gas-liquid mass transfer. In future, we might expect to see a greater attention being focused on monolith reactors in both academia and industry.